Hello everyone, welcome back. I hope all of you are doing good. In this video, we will be discussing the group 16 elements of the P block, in which we will be trying to do a general discussion in the physical and the chemical properties of this particular group. We will not be discussing the specific elements. We'll be trying to do in our next videos. In this particular video, we will be trying to understand that how do we understand the variations in the physical and the chemical properties of group 16 elements, and how do they vary, and what is the reason behind. So as we know that group 16 elements consist of 5 elements, that is oxygen, sulfur, selenium, tellurium, and polonium. Okay. And remember that these elements are also called chalcogens, okay, which simply means ore forming. Okay. Chalcogen is a Greek word basically for brass, okay, which points out the association of the sulfur with copper and its cogeners with copper. Okay, so let us try to discuss the group 16 element and try to understand what are their various physical and chemical properties. So starting with the first member, obviously oxygen is the first member of this group 16, or we call it Roman 6a of the periodic table. It consists of 5 elements, as I have already told you, that it is oxygen, sulfur, selenium, tellurium, and polonium. Okay, as I have already mentioned that this particular group is also known as chalcogens, okay, which means ore forming. And remember that out of this 5 element, polonium is radioactive, okay, which has a very short half-life. Now coming for the electronic configuration of this particular group. So these are the electronic configuration of this particular group. You can clearly see coming for oxygen atomic number 8 is 1s2, 2s2, 2p4, which can be written as He 2s2, 2p4 in brief. Okay, 1s2 represent, or the 1s2 instead of writing as 1s2, we can write as He, that is the nearest noble gas or the noble gas configuration. Sulfur is atomic number 16, which we can write as 1s2, 2s2, 2p6, 3s2, 3p4, or instead of that writing the long configuration, we can write in short as Ne, which stands for 1s2, 2s2, 2p6, and 3s2 and 3p4 is the outer shell configuration. In the very same way for selenium, you can see we can write as argon 3d10, 4s2, 4p4. Tellurium we can write as krypton 4d10, 5s2, 5p4, and polonium we can write as xenon 4f14, 5d10, 6s2, 6p4. Okay, if you see their electronic atomic number, you can see 8, 16, 34, 52, and 84. As I have mentioned in my previous video also, when we have done for group 15, that whenever you go from one element to another, the best way to get the atomic number is by adding the first element, that is the second period element, to third period element by adding 8. From third to fourth, you add 18. From fourth to fifth, you add 18. From fifth to sixth, you add 32. So basically, if you add 8, 18, 18, and 32, you get the next atomic number. So you don't have to memorize it. Okay. So if you see the configuration of this particular elements, you can clearly see that there is S2 and P4. In the last shell, you will see that there will be 2 subshell, which is S and P. In S, you'll always have 2 electrons, and in P subshell, you will have 4 electrons. So the general configuration, if you see, it will be NS2, NP4. So the general outer electronic configuration of this whole group elements will be NS2, NP4, where N is the principal quantum number. Coming next for the oxidation state. Okay, this group shows both the negative and positive oxidation state. If we talk about positive oxidation state, there are three positive oxidation state, which it shows +2, +4, and +6. The most common is +4 and +6, as we can see from its configuration also, ns2 np4. Either it can give 4 electrons of the p subshell or 2 more from the s subshell, making it 6. Okay, so these two oxidation state are the most common oxidation state, which it shows in various compounds formed by this particular group members. And as we have discussed in our group 15, the video where we have discussed group 15 elements, I have told you that whenever we move down the group, the higher oxidation state becomes less stable and the lower oxidation state tends to become more stable. And the reason for that is nothing but inert pair effect, which is nothing but a direct consequence of the post shielding effect of d and f orbital present in the heavier element. For those of you who have not watched those videos, please watch the video on group 15 elements for better understanding of inert pair effect. Okay, so remember that whenever we talk about group 16 elements, +4 and +6 are the two very common oxidation state, which will be seeing in most of its compounds. But +4 tends to become more stable as you move down the group. So the lower element tend to show +4 instead of +6. So why it happens is because of inert pair effect, and it's a direct consequence of shielding effect. Okay, poor shielding effect of d and f orbital in the heavier elements. So do watch the video on group 15. If you have missed that particular video, you will be understanding what is inert pair effect in very much detail. Now coming for the next, which is negative oxidation state. Remember that the negative oxidation state which this group will show is -2. Okay, but why they show -2? It is again clear from the configuration. It has ns2 np4 configuration. ns2 np4 means it just require 2 more to actually complete its octet, the nearest noble gas configuration, as a result of which it will have a tendency to gain 2 electron. But this tendency to take 2 electron, or the tendency to show -2 oxidation state, decreases as we move down the group. Obviously, because as we move down the group, the electronegativity will decrease, electron gain enthalpy will decrease. As a result, the tendency to take electron will decrease. Okay, as a result, oxygen usually shows -2 oxidation state. And not only that, oxygen only shows -2. Okay, oxygen being very electronegative, the second most electronegative element, it prefers to show only -2 only. Only in one of the compound it shows positive oxidation state, and that is the fluoride of oxygen. Okay, where it tends to show +2. Okay, which is nothing but OF2, because fluorine being more electronegative than oxygen, so oxygen shows positive oxidation state. Other than that, oxygen always shows -1. Okay, there are some exception in which in some cases, like in case of peroxide, where it shows -1, but in general it always shows -2 oxidation state. Okay, now coming for the anomalous property of oxygen, as we have discussed in our previous videos also, that the first element of any group always shows anomalous properties. Okay, what we have seen in nitrogen also, and the reasons of actually oxygen being very much different from the other members, showing different properties than the other members of the group, are because of its small size. Oxygen is very small, because of which it will actually have very, very high electronegativity, very high ionization enthalpy. And remember that being the element of the second period, okay, since it has the maximum principal quantum number 2, and for principal quantum number 2, we have only S and P subshell. We don't have any D subshell. So there will be no D orbital for this particular atom. As a result, there will be no empty D orbital. There will be no availability of D orbital for bonding. As a result of which, this particular system cannot expand their covalency. Okay, we'll be trying to see that in detail. So coming for the main properties in which oxygen differs from the rest of the members are, the first one, as very much similar to nitrogen, oxygen is diatomic, and unlike other elements of this group, in this particular group, oxygen is the only one which exists as O2. Okay, the other members will not exist as O2, like sulfur exists as S8, octaatomic, but oxygen tends to exist as O2. Now, why it is so? It was found out that it is because of the small size and high electronegativity, where oxygen will be able to form p-pi double bond. Okay, as I've already mentioned that in case of nitrogen also, Again, I am repeating it. If you have missed those videos on group 15, please watch that. Okay, over there we have done a detailed discussion in all those in all these topics. Again, if you have missed that, always remember that if you see the configuration of oxygen, oxygen is 1s2, 2s2, 2p4. When you write 2p4 configuration, you will have two orbitals with half filled electrons. Okay, as a result of which what will happen is this orbital can easily form bond. So there are two p orbitals which are half filled. One of them will form a pi bond, sorry, sigma bond, direct overlapping, and the another one which will be left, the p orbital, will form pi bond, bilateral overlapping. But remember that this is possible only if the two atoms come very close to one another, so that this p orbital which are left will form actually lateral overlapping. And that is possible in oxygen because of its small size. If you go down the group for sulfur or selenium or tellurium, what will happen is as the size increase, there will be no effective overlapping. Although they can form a sigma bond, but they cannot overlap because their size is big. As a result, they cannot come very close to one another for effective overlapping. As a result of which, they will not be able to form multiple bonds, double bonds. And since this double bond or pi bond is formed by two p orbital overlapping with one another, that's why we call it p pi double bond. Okay, so remember that that is the reason why oxygen exists as diatomic molecule, okay, with a double bond between the two atoms. Oxygen is a gas, while the other members of this particular group is not gas, they are solid, like sulfur is a solid. Now, why oxygen is a gas? The intermolecular force, okay, which is there between two O2 molecule, okay, is van der Waals force, which is very weak, as a result of which it can be easily broken down by collision at room temperature. As a result, they easily break, and when they break, they exist as gases, obviously, at room temperature. Okay. Oxygen is restricted to covalency of 4, but rarely it shows covalency of 4. In practice, it shows an oxidation state of 2. Okay, so maximum it can go for 4 theoretically, but in practice it always shows oxidation state of 2. But remember that if you take other element of this group like sulfur, selenium, tellurium, they can exceed the the covalency of 4 and go beyond that also. They can go for 6 also. Now, why it is not possible for oxygen? As I've already mentioned, that it is because of non-availability of d orbital. Okay, there is no d orbital in its valence shell which will help it to expand its octet, while rest of the element, since they belong from actually in period 3 or 4 or 5 or 6, all these particular period elements will have d orbital in their valence shell, if you talk about p block elements. Okay, coming for hydrogen bonding. Okay, oxygen is very small and has quite high electronegativity, okay, nuclear charge, and because of which it can form very strong hydrogen bond. Okay, but the other element of this group being very, or they have very low electronegativity compared to oxygen, and obviously because of their very big size, as a result they will not be able to form hydrogen bond. Okay, that is why, okay, a very common actually point to make in this particular topic is H2O is a liquid. Okay, if you see H2O exists as a liquid, but the same compound, the same type of compound for sulfur, that is H2S, the same hydride, but for sulfur is existing as a gas. Why it is so? Because H2O can form hydrogen bonding because of the oxygen, because of the high electronegativity of oxygen, while H2S, because of low electronegativity of sulfur, will not be able to form the hydrogen bonding, as a result of which what will happen is it will exist as a gas. Okay, so very common why H2O exists as a liquid where H2S is a gas. It's because of the oxygen, which actually is very high electronegativity, having very high electronegativity, can easily form hydrogen bonding. Okay, coming for the trends in chemical reactivity. Okay, so what are the trends in chemical reactivity? How does it vary? So we'll try to take 3 trends. Okay, reactivity with hydrogen, reactivity with oxygen, and finally we'll come for halides. Okay, so let us start with reactivity towards hydrogen. So as I've already mentioned before also, that whenever a compound forms compound, or whenever an element forms compound with hydrogen, we call it hydride. So basically it is the formation of hydride. So what kind of hydride this particular group members form? They always form hydride of this type. Okay, it's a volatile hydride of the form H2E. Okay, all hydrides are bent shape. So remember that all the hydrides will be bent shape, and E over there is nothing but the element of this group. Okay, it can be H2O, H2S, H2SE, H2TE, or H2PO. Okay, and all of them will have bent shape. And remember that if you try to find out that which one of them will be more acidic, okay, whether H2O or H2PO, it was found out that H2PO will be more acidic. That means when you move down the group, the acidic character of the hydrides will increase. Now, why it is so? It is because of the low bond dissociation energy. Try to understand. As we have already discussed in group 15 elements also, when we move down the group, the atomic size increases. When atomic size increases, the distance between the oxygen and the hydrogen, or the element and the hydrogen, whatever element you take, will actually be going on increasing. So oxygen and hydrogen will be having very short distance, where sulfur and hydrogen will have a long distance. Then it will increase more and increase more and increase more. That means the bond length will increase. And as we know that if bond length will increase, bond dissociation energy, the energy required to break it, will be very less. It will break very easily. Now, if a system is acidic, it must be able to give H plus very easily. So obviously, if the bond will break easily, the H plus will be furnished very easily. As a result, the system will be more acidic. So if you compare over here, obviously H2O having a very short bond length will have a very high bond dissociation energy. As a result, it will be least acidic, whereas H2PO being the biggest, HPO being the biggest in size, obviously will have the longest bond length, so will have the least bond dissociation energy, so breaks very easily. So it will furnish H plus very easily, so will be the most acidic. Then coming for the thermal stability, again, just the opposite, the same concept, just the opposite discussion now. So whenever you have H2O and H2PO, just now what we have discussed is the bond dissociation energy will decrease as we move down the group. So it will break easily. So when I heat this particular hydride, so obviously with the one which will have the longest bond length will decompose faster. Okay. As a result, H2PO will be the least thermal stability, will have the least thermal stability if you compare with the others. So H2O will be the most stable and H2PO will be the least stable hydride. Okay. And finally, coming for the reducing character. Okay. Again, the same discussion. Whenever you move down the group, it is very easy for the bond to break. When the bond will decompose, it will easily furnish hydrogen ion, so or hydrogen. So when a system will furnish easily hydrogen, obviously it will be a better reducing agent. H2O, since it is thermally very stable, so will not break easily. Bond length is very short, so bond dissociation energy is very high, so will not be able to furnish very easily the hydrogen atom. As a result of which H2O will be very poor reducing, will have a very poor reducing character, whereas H2PO will be having a very high reducing character. Okay, so it will increase down the group. So a very important topic. So remember that. That is how actually we know the chemical trends in chemical reactivity if we talk about the formation of hydrides, okay, and how they vary in their chemical properties or in their physical properties. Then reactivity towards halogen, okay. So obviously when they react with halogen, they form halides. So what kind of halides they form? They form a large number of halides. Some of them are EX6, EX4, and EX2. These are the most common one, where it is showing an oxidation state of +2. In EX4 +4 and EX6 it will be +6. Okay, these are the three common oxidation state which this particular element shows. Okay, the stability of hydride decreases in the order fluoride, chloride, bromide, and iodide. Again, it is the same discussion. It is because of the size. As the size will increase, so the halide, if you take fluoride, okay, or if you take chloride or bromide and iodide, the fluoride will be very stable because of its smaller size. It will form a stronger bond compared to chloride. Then bromide and iodide being the largest, obviously form very weak bond, so it will be the least stable. Okay. Among hexafluoride, so if you talk about EX6, remember that hexafluoride among hexahalides, sorry, if you form EX6, then the hexafluorides will be the most stable, or the only stable fluorides. Okay, the other fluorides will not be stable. So if you talk about hexahalides, then only fluorides will be stable. Okay, and of this, remember that all of this particular EX6 will have octahedral structure, okay, all the hexahalides. And out of this, SF6, okay, is very stable, exceptionally stable, okay. It is because of some steric factors, okay, and because of which, okay, since it is very, very stable and it is very inert, it will not react even at very high temperature, okay. It does not react with water. It is non-poisonous, okay. It does not have any smell. It does not decompose. As a result of which, this particular SF6 is used as an insulator in high voltage generators and switch gears, okay. So remember that SF6 actually is very, very stable, okay, and it is because of the steric factors. Now coming for the reactivity towards oxygen, that is formation of oxides. These are the two types of oxide which they form, EO2 and EO3. In EO2, AE is having an oxidation state of plus 4, whereas EO3, it will have an oxidation state of plus 6. These are the two common oxidation state as already mentioned. Okay, and remember that both the oxide, whether it is EO2 and EO3, will be acidic in nature. Okay, usually non-metallic oxide will be acidic in nature. And out of this, okay, if you take O3 and SO2, okay, if you take ozone and sulfur dioxide, they are gases, whereas SeO2, okay, that is selenium oxide, will exist as solid. So these are the various basic trends in chemical reactivity and physical properties, okay, of group 16 elements. Okay, so that is how actually we can understand how does group 16 elements actually varies in its physical and chemical properties. What are its oxidation state, what are its electronic configuration, what are the various how does it react with hydrogen, oxygen, or halides, and how does the property vary as we move in the group. So that's all about the group 16 elements, the general trends in group 16 elements. So thank you, everyone. Do subscribe for this channel for the various explanation in chemistry. So thank you.